Hello, my name is Jacob Marks. I'm going to be presenting on campus Wi-Fi fingerprinting. Smart campuses are an ever-increasing trend in the world. These smart campuses involve much more expressive maps, much more Internet of Things devices spread around the campus, and they can use things like tracking to try and keep track of where students or faculty are. So what this is for is it can help visitors find things, it can help faculty and students on the campus find things on campus and find out what events are happening, and the tracking can be used voluntarily to help with track class participation, uh, other events the student might need to go to, or even track what parking is available on campus. Now, the trouble is, GPS might not always work on smartphones inside buildings, especially the kind of large multi-story buildings that are common on many campuses. So how do we track inside buildings? Well, the answer is Wi-Fi fingerprinting. But another issue is, how do we visualize all this data that we'll be getting? In order for a smart campus to be useful, we need ways for this data to be visible to anybody who's using it, even somebody who's not a computer scientist or somebody who's not used to the data. So Wi-Fi fingerprinting uses Wi-Fi signals when GPS isn't available. One common technique would use triangulation to try and find the location of somebody using up to 3 or more signals. Now the trouble is, 3 or more signals might not always be available, and there are several other issues. The strength of a Wi-Fi signal does not always indicate the exact distance that a person is from that wireless access point. So, we need other ways to try and detect the person's location. So why not use machine learning or other types of learning algorithms to try and predict somebody's location based on the wireless access point data? Well, there's been a lot of research into this field. UGI, the University of Jammu the First, has had a smart campus that they've been trying to get up and running for a long time. So on their website, you can find a much more expressive 3D map, and you can also find their data sets that they've tried to use for Wi-Fi fingerprinting on the campus. So this is the data set that I decided to use for mine. One thing that's very helpful about it is that the buildings in this image here are very, very different from each other. This one here has 4 floors, this building has 4 floors as well, and this one has 5 floors. They're close together, which makes it a little more difficult to try and track exactly where somebody would be inside these different buildings. But their very interesting shape helps with noticing which part of the data is from where. It's much easier to tell when the buildings aren't just simple squares. Now, the data set that's being used has over 21,000 different instances and 529 attributes. Those attributes involve 520 wireless access point signals. So each of these has a measurement of the strengths, and it also says whether that signal wasn't visible or not. Alongside this, there's the longitude, the latitude, a building ID visible in this graph, the floor where the data was taken, there's also a space ID, and a user ID, and a phone ID. Now the user, phone, and a couple of others are useless data because they don't contribute to the different models. Now the space ID, the intention was to identify specific rooms, which would be incredibly useful to identify, but the trouble with the dataset is that many of these values are null, which is why for this project I've decided to only focus on trying to identify the building ID and the floor that's being used. So one thing that's helpful to do is to visualize this data in 3D. So you can see that there's a whole lot of rooms in this kind of center building here, and the 5 floors here are very close to this building here, which makes it a lot more difficult to get a reading. Now, many of these are just in hallways and not walking around inside the various rooms, which can also make it difficult because presumably many of these wireless access points are inside the rooms. So for my predictions, I used orange. I used 3 different models. I used a neural network, random forest, and k nearest neighbors. The neural network has 100 nodes per hidden layer. The random forest has 10 different decision trees, and k nearest neighbors looks out for 5 neighbors closest to it. Each of these were evaluated, and then I was able to process the data later in Python. Perhaps the largest part of this project has been the visualizations. So one thing you can see in these graphs here is the Wi-Fi coverage for a number of different access points. So for example, in this one, in wireless access point 405, we can see it is only covering one tiny section of this building. That's just a couple of different data points, which means that if we detect it, it may be extremely useful for detecting which floor and building we're at, but for the most part, that data is being unused. It's a column full of a lot of null values. However, in this figure, we can see that the wireless coverage for wireless access point 495 is immense. It covers almost this entire building, which means that if we detect it, it doesn't actually mean that much. We can tell we're in this building, but it's very difficult to tell which floor we're at. Another useful visualization technique I found was visualizing the wireless access points, all of them using these bubbles. The colors don't matter, but the size does, and that indicates the strengths. Their position is based on the average longitude and latitude of all the different data points where that wireless access point was seen. And one thing we can see is that there's some sections of the map that are extremely sparse, or the wireless access points are stretched very thin. And one thing that's very helpful is visualizing this in 3D. So when we view it in 3D, we can see that some of them are spread between many different floors and are almost seen in the center of the building. So these wireless access points are useful for identifying the building that they're in, but again, not very useful for identifying the floor. Well, in certain situations like this, we can see them actually spreading between the 2 buildings, which can be troubling because then seeing a wireless access point might tell us we're in this middle building when actually we're in this 3rd building here. Now, one thing I wanted to do with all my graphs was to try and make them colorblind friendly, because one thing I wanted was visualizations that could be used by anybody and could be understood by anybody using them. So I tried to keep all the colors in one simple gradient, or having where the color doesn't matter, like in this graph. So what were my results? Well, for the building ID, I had extremely good results. The neural network, random forest, and k nearest neighbors all had a greater than 0.92 accuracy. However, the floor classification was much worse. So at the lowest, we have k nearest neighbors with a 0.3, and at the highest, the neural network with a 0.78. And one thing that's extremely helpful is ways to visualize this data. Are there certain points that are bad? Which points are there? So here, in the top row, we can see the different classifications for the building ID. The purple dots are the errors, and the yellow are correct. So neural network did extremely well, very few errors, while the random forest and k nearest neighbors both did a bit worse. In the bottom row, we have the floor predictions, and you can already start seeing certain sections that are very difficult to tell what's happening. Like this corridor here seems to be a problem, and this middle segment also seems to be a problem. Now, the distribution of the floors is interesting because you can see it is still predominantly accurate classification, but we can also see it falling off as it predicts the different floors. But 3D visualizations really work far better with this. So in this figure, we can see this 3D visualization of the different classifications in neural network. And now we can very clearly see that some of them are in very specific segments. It's much easier to see that in this 2nd floor, we have a lot of trouble in the 2nd building, while at the very top floor on the leftmost building, we have a lot of trouble. So I believe that these kind of 3D visualizations are necessary to get a good understanding of the building layout and which sections of the building may be especially hard to classify. In this figure, we can see the classifications for k nearest neighbor, and the dots represent where they were predicted, while the lines are drawn to where they were actually located. So we can see one outlier here that was completely off. It said it was on the bottom floor when actually it was on the top floor. While for many others, they're only off by one floor. Now, only being off by one floor isn't actually very bad, because in an actual use case, this would be following a person as they moved about campus, and we would have many data points. We would have them over time, and we would be able to see where the person was moving. So in this way, it wouldn't make any sense for the person to suddenly leap up 2 floors or suddenly move to another building without having data points in between. So in many ways, this data is actually very good. So the building ID is predicted extremely well, but why isn't the floor? Well, my assumption is that the Wi-Fi signal can very easily spread through the floor or the ceiling and makes it much more difficult to tell exactly which wireless access points are on someone's floor. Now, ways around this are simply having more data, knowing the locations of wireless access points, or following the person over time, and also using the some longitude and latitude values that we can get. Though GPS doesn't work very well inside, it does work sometimes, and that data could be used to much more accurately predict what's going on. So in conclusion, smart campuses are the future. We're going to see a much more connected campus with much more use of Internet of Things concepts and smartphone applications to try and keep track of important school activities. Now the trouble is, the GPS does not always work, but in those situations, its Wi-Fi is very promising for predicting a location on campus. Now in my data, neural network worked best. However, neural network also has a lot of limitations. It's more difficult to run and much more difficult to set up. And another issue with many of these applications is that if a wireless access point is moved, or if there's changes in the building, even something as simple as furniture moving, that could have a drastic effect on the data set, as now the wireless access point signals are going to be very different throughout the campus. So in all these situations, data would need to be constantly collected, and it would also need to be constantly updated and processed. Now this is where visualizations come in. Visualizations are extremely important for identifying hotspots around campus that are very difficult to understand. So we might have a certain hallway that has too many wireless access points and the signal is misunderstood, or maybe there's too few, or it's not spreading very far, or the architecture is confusing the processes. So for all of these, using a visualization can help us understand the different issues and then cope with those issues. We can either collect more data or even modify that part of campus by moving a wireless access point. So my primary sources involved the dataset from UGI and their own sources showing off their smart campus. Also, CATBA with predicting indoor location using Wi-Fi fingerprinting was very useful for finding this dataset in the first place and also understanding more of how to use it. Thank you.